Okay, this is work and power in rotating systems. Remember that the equation for work in translational systems is work is the force times the distance. That equation right there. What we do is we substitute torque for the force and substitute angular displacement for displacement, and we get this equation. Okay? So really important that we realize that the equation that we're going to use for rotational systems is this equation right here. All right? Where this is the torque and this is the angular displacement. So really similar to the work in the translational systems world, but this is the work for rotational systems. Also, power, very similar. Power is still the work divided by the time. This is a differential equation version of the power equation. So we substitute the torque for the force, substitute angular velocity for the velocity, and the equation that we use for power in the rotational world is that the power is equal to the torque times the angular velocity. So we still use the conservation of energy equations, but now we also have rotational kinetic energy. Let's try this problem. A rotating flywheel provides power to a machine. The flywheel is originally rotating at 2,500 revolutions per minute. The flywheel is a solid cylinder of mass 1,250 kilograms and diameter of 0.75 meters. If the machine requires an average power of 12 kilowatts, for how long can the flywheel provide power? So the equation that we will use is the power is equal to work divided by time. Where now we've got to look for the time, so that equation is work divided by the power. Since this is rotational, I'm going to use a rotational kinetic energy, and I'm going to divide that by the power. The rotational kinetic energy is 1/2 I omega squared divided by the power, where the I, because this is going to be treated as a solid disk or solid cylinder, I is equal to 1/2 omega r mr squared, I should say. That should be an m. That should be mr squared. So my power therefore is equal to 1/2 times 1/2 mr squared times omega squared. And I'm dividing that once again by the power. And the only thing that we really have to fix here, now this is the time, I should say. This should actually say the time, so let me take this off. This is the time, is what we're solving for here. And the only thing that we need to convert is this angular velocity, where they've given us 2,500 revolutions per minute. We need to convert that to so that we eventually get radians per second. We want to convert 1 revolution to pi radians, and then in 1 minute there are 60 seconds, I should say. There are 60 seconds. So the minutes cancel, the revolutions cancel, and our answer will give us something along the lines of radians per second. So this will equal some value in radians per second. We said before we'll plug it into there. Our value for M is 1,250 kilograms. That's what we'll plug in for M. For R, we've been given the diameter, so we take 0.75 and divide that by 2 meters, or by 2, and the units are in meters. Our power is 12,000 watts. And we'll plug that into there, and plug that into there. So that's how we go about solving that particular problem. Then this next problem says a uniform rod of mass M and length L rotates around a pin through one end. It is released from rest at the horizontal position. What is the angular speed when it reaches the lowest point? What is the angular speed of the lowest point of this rod at this position? What is the linear speed of the lowest point of the rod in this position? So here's what's happening. Here's this rod. Oops. Here's this rod, and it's going to rotate about this position there. It's got a length L. And we want to know what happens when it rotates downward by gravity. So its center of mass starts off here. Its center of mass starts off here and rotates down to that point. And the end will rotate down to that point. What we essentially want to do is we want to use our energy model, and at first we got all gravitational potential energy, and everything is staying within our system. Everything's staying in our system. We've got the Earth, and we've got this rod. It's going about this hinge, so we can just include everything. Everything's staying in our system. Nothing's going into the system. Nothing's coming out of the system. At the end, all this gravitational potential energy is being turned into kinetic energy, but of the rotational kind. So essentially what we can say here is that the gravitational potential energy is turning into rotational kinetic energy. So that's essentially mgh is equal to 1/2 I omega squared. Now, we need to look at certain things. This h here, the total distance that the center of mass travels is a distance L over 2. So this h is going to be L over 2. I is going to be the rotational inertia for a rod on its end, which we've said before is 1/3 ml squared times omega squared. If we solve this equation, we notice that the m's cancel. One of the L's on each side cancel. The 1/2s cancel. And we get an equation of omega is equal to the square root of 3g over L. This answer is the angular speed everywhere along the rod. To find the linear speed, we use our bridge equation, which says V is equal to omega R. But in this case, this R we replace with L. So that's V is equal to omega L, because we want the velocity at this point here. In that case, we replace the omega with what we solved for in the previous part of the equation, and we get the square root of 3GL times L, and that ends up equaling the square root of 3GL. So this is actually the linear speed. This is the linear speed of end of the rod. So that's the speed V when it gets to this spot right there.